Han Solo is cool. Like, really cool. Like, shoot first and ask questions later cool. Like, he's about 60% of why I love Star Wars cool. But I think I found something that makes him even cooler. Let me show you what I mean. I'm going to pose a thought experiment. Imagine two twins. Let's take this one and put him on Earth, where he'll live with his family in a lovely suburban home in Atlanta, Georgia. But this one, we're going to put him on a rocket ship and send him off into the far reaches of space. We'll send him faster than we as humans right now have any real idea of traveling, at 99.9% of the speed of light. We can send him out for 5 years. It sounds boring, I know, but he can play cards with the onboard AI or whatever. At this speed, while our twin back on home planet Earth is growing into middle age with his lovely family, experiencing time at its typical constant rate, our intrepid space explorer is experiencing 4.5% of the time, and therefore aging, that the other twin does. What does this mean? It means that, after the 5-year journey that twin number 2 goes through, twin number 1 will have had time to have children, grandchildren, grow to a ripe old age, and even die before his brother returns, as the 5 years that the second twin is aged is dwarfed by the 110 that twin number 1 has experienced. Yet the younger of the two only traveled through space. So how could this happen? Seems to make no sense, right? Well, it can. Make sense, I mean. But I'm going to have to dig a little deeper to make it so. Albert Einstein was a theoretical physicist born in 1879, Germany. Among his numerous contributions to his field, in 1905 he determined that the laws of physics are the same for all non-accelerating observers. This essentially means that if you're not speeding up, physics are acting the same for you as everyone else who is also not speeding up. He also determined that the speed of light in a vacuum, meaning a space with no other interference, i.e., space, is independent of the motion of all observers, meaning light always travels at the same rate when not obstructed by or traveling through some other medium, like air or water, for example. These things essentially make up the theory of special relativity. For Einstein's time, it introduced a new framework for all of physics. Building on this, Einstein spent the next 10 years trying to include acceleration in this theory, and, in 1915, published his theory of general relativity. In it, he determined that massive objects cause a distortion in space and in time, which is felt as gravity. Let me explain that a little more. Two objects exert a force of attraction on one another, known as gravity. The force tugging between the two bodies depends on how massive each one is and how far apart the two lie, as determined by Sir Isaac Newton. Even as the center of the Earth is pulling you toward it, keeping your feet on the ground, your center of mass is pulling back the Earth. The more massive body barely feels the tug from you, while your much smaller mass finds yourself much more firmly rooted thanks to that same force. Yet Newton's laws assume that gravity is an innate force of an object that can act over a distance. Albert Einstein, in special relativity, found that space and time were interwoven into a single continuum, known as spacetime. Events that occur at the same time for one observer could occur at different times for another. Let me say that again. Time is relative. As he worked out the equations for his general theory of relativity, Einstein realized that massive objects cause a distortion in space-time. Imagine, if you will, setting a large rock in the center of a trampoline. The rock would press down into the trampoline surface, causing it to droop. A marble rolled around the edge would spiral inward toward the rock. Now imagine this with the sun and our own planet Earth. Planets circle around the sun, and things fall because space curves. As we determined, space and time are the same continuum. So, if space curves around massive objects, we can thusly say that time curves as well. Why is this interesting? Well, because Einstein's special theory of relativity also shows us that something else that's pretty important to this video. As an object accelerates, its relativistic mass increases. So, as an object accelerates, it gains more mass around which space bends, and time bends with it also, which means that the faster an object moves, the less time is experienced by the object. Time dilates as an object accelerates. Cool, right? Meet the greatest time traveler in human history. Sergei Krikalev, Russian cosmonaut, spent a total of 803 days, 9 hours, and 39 minutes orbiting Earth at 17,500 miles an hour. And, due to time dilation, Sergei time traveled into his own future by 0.02 seconds. Now, I understand. 0.02 seconds doesn't seem that impressive. But the sheer fact that this happens at all is monumental to physics today. Due to the previously mentioned relativity, we know that, had Sergei been traveling even faster, his time travel chops would be much more respectable. So, let's take this back to our favorite space pirate. Han Solo describes the Millennium Falcon as having made the Kessel Run in 12 parsecs. But, well, sorry to break it to you, this is kind of meaningless. Well, sort of. The way Han Solo uses this phrase implies that, as his ship is so fast, he's able to travel this run in such a short amount of time. Only, there's one problem with this claim. A parsec is not a unit of time. It's a measure of distance. This mistake on the part of the Star Wars writers is ubiquitous among fans, and is explained away in the expanded universe by black hole slinging or some such. But, if the Kessel Run that Solo made really is 12 parsecs traveled, how far is that? Alright, while the true definition is a bit technical, a parsec is essentially the radius of the Earth's orbit around the Sun, or 3.26 light years, which doesn't seem that bad, but considering that 1 light year, the amount of distance that light, the fastest thing we can track, travels in 1 year, is this many miles, 1 parsec is pretty big. 1 parsec is this many miles, which means our 12 parsec journey done by Captain Solo is 229,966,912,567,200 miles, which is a lot. If you were traveling the Kessel Run in your RV at 80 miles per hour, it would take you over 328 million years, which of course isn't great. I most definitely don't have that kind of time. Like, I have homework. Funnily enough, Han Solo doesn't seem to have that kind of time either, as he spends a fair chunk of his time flying in the Star Wars film traveling at the speed of light, which, in case you need a refresher, is freaking fast. 299,792,458 meters per second, to be exact. Without the sciencey explanation, it's impossible for an object with, mass to travel at such ridiculous speed. It's the universal speed limit, and nothing can outrun it, not even the beautiful piece of work that is the Falcon. But we want to give our intrepid smuggler the best chance we can, so we'll play around with just a bit with the reality of the situation, and say that Han Solo is going to be traveling at 99.9999999% the speed of light. Why does this matter? It matters because we want to use this amount to figure out, using a time dilation equation determined by a pre-Einsteinian physicist named Heinrich Lorentz, to see just how much time Han Solo is experiencing while he's off flying through the Kessel Run. In this equation, this first t is the amount of time passing for a stationary observer. Essentially, this is how much time Solo's Kessel Run would take according to anyone who was not on the Falcon at the time. This is the time experienced by Luke, Yoda, and Obi-Wan. V is the velocity of the Falcon, which, as mentioned before, we have decided to be 99.9999999% the speed of light. C is the speed of light in a vacuum, which is 186,000 miles per second. T is what we want to figure out, as it's equal to the amount of time passing for our space cowboy and his Wookiee sidekick. Plugging in all of our values and doing a bit of algebra gives us our results. Are you ready? They're pretty fun. I'll spare you the more fiddly details, but for Han Solo, his beloved ship is taking him through those 12 parsecs in about 15 hours. Great! He can spend his time letting the Wookiee win a few games of space cards. But, as I'm sure you can see this going towards, if the Kessel Run is 12 parsecs or 39.6 light years long, a ship traveling nearly light speed would take more than 39.6 years to get there. That's 40 years that the Millennium Falcon is light skipping through. For every 15 hours Solo spends on the run, he loses a bit less than half a century in everyone else's time. This means that, given this theory were true, if making the run at about the age of 29, Solo would be more than twice as old as he looks. He would have lived through the Clone Wars, the fall of the Jedi Order, 2 Death Stars, and the rise and fall of the Empire. And, to top this all off, if Han Solo made his famous 12-parsec Kessel Run around the age of 29, he'd be even older than Anakin Skywalker, who was about 42 at the time that Solo meets Anakin's old master and his son in that iconic dimly lit cantina a long time ago in a galaxy far, far away. So, thanks to relativistic physics, we can most certainly say that the chances of him being far older than he appears are pretty dang high.